Okay, this is video 30.2. We're going to be looking at the magnetic field of current loops. This is a topic where we're going to be using the Biot-Savart law, but we'll find that it's much easier. The integrals are not a huge pain like they were for the infinitely long wire. So we'll start with a circular arc. Not a complete circle, but an arc of radius r that subtends an angle theta. And we're going to measure theta in radians. Don't get freaked out by that. And we'll say that this segment of wire carries current I. And we want to find the field at the center of the arc, which is relatively easy to do. Finding the field anywhere else is a pain, but at the center of the arc, it's not too bad. So what we'll do is Biot-Savart law. We break the arc up into a lot of small ds's, and the r vector points that way. And Biot-Savart also says dB equals mu naught I over 4 pi r, or 4 pi times r across ds. No, not r across ds. ds cross r divided by the magnitude of r cubed. Now first we'll get the direction. ds cross r. Index finger in the direction of ds, other three fingers in the direction of r, and the magnetic field at the center of the arc, in this case, points out of the page. And it will point out of the page for every single ds along this arc. Now the other thing is that because ds and r are perpendicular, the magnitude of ds cross r is just rds. So dB becomes mu naught I over 4 pi times rds over r cubed, divide top and bottom by r, and then we have to integrate. So b equals mu naught I over 4 pi, and because r is the same for every point along this arc, we can bring that r squared out of the front of the integral, and we're just left with the integral of ds, which is simply the arc length. So the total length of the wire. And that equals r times theta if theta is measured in radians. And so that means the magnetic field at the center of the circle, or the center of the arc, mu naught I theta over 4 pi r. Not something you should probably memorize, but useful. What's more useful is what happens when we make that into a complete circle. Now, a complete circle is just an arc where theta equals 2 pi, and so b becomes mu naught I times 2 pi over 4 pi r, and it just becomes mu naught I over 2r for a complete circle. Now, a useful thing here. We've got that current loop. We said that when the field was, or the current was going, this is basically counterclockwise, the field points out of the page. And there's a useful shortcut. It's another variant of the right-hand rule. If you curl your fingers in the direction of the current, your thumb points in the direction of the field at the center. So if you do that, curl your fingers counterclockwise, you'll find that your thumb is pointing out of your computer screen. That is something you need to know, because current loops are quite common, and you'll have to know the direction of the field even when you don't necessarily need to know its magnitude. And an example here, this is problem 9. I'll draw that figure. What we've got is a current loop. Looks like this. Carries current I in that direction. We're trying to find the field at point P. That angle is theta. This radius is A. And that outer radius is B. And so there are 4 different segments of wire here. We want to find the field at P due to all of them. I'm going to label them 1, 2, 3, and 4. Now the fields of 1 and 3, we'll get those using the equation we just derived earlier in this video. But first let's look at the fields of 2 and 4. Notice that for example 2, R points that way, and ds points in the opposite direction. Whereas for wire 4, ds and R point in the same direction. But since we're doing a cross product between ds and R, both of those end up being 0, because when you have the cross product of 2 parallel vectors, that ends up being 0. For 2 and 4, ds cross R equals 0, and so the fields of those 2 segments are nothing. Now the field of arc 1 has a magnitude of mu naught I theta over 4 pi times A, and its direction, if we curl our fingers counterclockwise, which is the direction of the current in arc 1, is out of the page. The field due to arc 3 is again mu naught I theta, but this time the radius is B. And that field excuse me, points into the page. If we add that all up, we find that the total magnetic field is mu naught I theta over 4 pi, 1 over A, minus 1 over B, and that points out of the page. And you can simplify that a little bit further if you want, but that's the answer. Tomorrow I'm going to check problems 6 and 7, which are sort of similar to this, but should be a little bit easier.